Okay. Okay, so now we're actually starting the class. Um, so two topics for today, so half and half. So, oh, and then the other thing I want to make an announcement before I start, which is that I'll send you email. We got the live streaming through Zoom of the Learning Glass working. It was actually working before. I didn't realize it was already working. So I'll send out a Zoom link for the Friday 8 a.m. session. So the Friday 8 a.m. session will be a live Zoom question and answer session. We don't have to run the whole time, and then the 9 o'clock will be just a regular recording session. So. Okay, so two topics for today. So the first is what's in the magnet, what makes noise in the magnet, and how is it kind of set up. We'll talk about 5 different things in the magnet that are relevant, and then the second part we talk about quantum mechanics. Now I don't know a lot of quantum mechanics, but we want to just talk about spin versus precession. Those are 2 different things. You don't want to get those mixed up. And in some respects, we'll find out that quantum mechanics is actually simpler than macroscopic mechanics. So, and that's fundamentally, the signal is fundamentally coming from this precession phenomenon. So let's get started. So first the magnet. So you know it's a really big magnet, and so I'll draw a really big magnet. So I need a lot of space. So here's the bore of the magnet. So there's the magnet sort of going through the top a little bit too high. So there we go. Okay, so we've got this gigantic donut, and so what's in there? So if you look inside the magnet, the thing that makes the magnetic field, the main magnetic field, are these superconducting coils. And so what they are is they're just a big bundle of wire. They've got a lot of wires in them. And there's a couple of them in there. It's like 4 of them in there, 4 bundles. And so those bundles of wires are bathed in liquid helium. And a long time ago, actually, right around the turn of the century, some physicists figured out that if you cool wires down, as you cool them down, the resistance to the flow of current through them gets less and less. But when you get down to about 4 degrees above absolute zero, suddenly the resistance goes to 0. Not just small, just 0. And so the way the magnet works is it's really sort of a strange thing. What happens is there's current in these coils, but it's not plugged in. So you might wonder, like, how do you get the current into the coils? Well, if you have a little transformer here, you could induce some current without touching the coil in the coil. And so you could sort of inject a bunch of current into the coil. But then, when you're done, you basically, it's not plugged in. The current just keeps going around just by itself. And so that's what actually makes it quite dangerous, because if you, if the power goes off and the lights go off and every single LED on the magnet is off, it's still on. The current's just going around and around by itself, making this huge magnetic field. And that huge magnetic field is the first piece. That's called the B0 field. So, and it's a strong field. Ours is a 3 Tesla, a 2.9 Tesla field. And, what is that, for instance, 3 Tesla. So what is the magnetic field of the Earth? It's like 25 to, depends on where you are, micro Tesla. So 60 millionths of a Tesla. That's the Earth. So it's a lot more than the Earth. And we need that field, we'll find out, to polarize the proton so we can detect this precession business. So that's the first part. And so we have to keep the refrigerator on. There's a 4 degrees above absolute zero refrigerator that keeps these wires very, very cold. So that's the B0 field. So when we're talking about magnetic fields, one thing that we will often talk about is electric current versus the magnetic field. And both of those things, electric current and the magnetic field, are a vector. And so there's a thing called the right-hand rule. So this is worthwhile keeping in mind. The right-hand rule, if your thumb of your right hand, so I'm in the learning glass, so I'm using my left hand, but it looks like a right hand. So this is the direction of the current. Then the tippy tips of your finger, so if this is the direction of the current, the tippy tips of your finger point in the direction of the magnetic field. It's at right angles to, the tips of your finger are at right angles to your thumb. So that's the right-hand rule. And so if we have current, so for instance in these guys, say the current is going up like that. So imagine we had the current going up this way. Nominally we call it a positive current. So if the positive current is going up like that, what does that do? Well, that makes the tip of the fingers point in this direction. And so that makes the B0 field. So the B0 field will be coming out this way. So that's the B0 vector field. And you get that from positive current going this way in the coils. So let's put up the coordinate system here. So the coordinate system, we have the z-axis coming out this way. So that's normally called the z-axis, and then the y-axis going up that way, and then the x-axis sort of coming out at you. So x-axis is left-right. So here's the x-axis. So when you're in the magnet, the z-axis is kind of horizontal, but a lot of times when people make pictures of spins, they make the z-axis go up and down. So I'll warn you when that happens. So, okay, so that's the first part, the B0 field. Then the second part is the part that makes the noise. And the part that makes the noise are the gradient coils. So the gradient coils are another big thing inside the magnet. So this weighs a couple tons. So it's another set of coils. You can't see it. It's actually sort of embedded in the magnet. So that's the gradient coils. And so what are the gradient coils? Well, they're something that changes the strength of the Z magnetic field. So that's an important thing. So what does that do? It modulates Z component of B. So, and then you have 3 different ones. You can modulate it in the x direction, the Z component in the x direction, or the Z component in the y direction, or the Z component in the Z direction. So how does it do that? Well, it just has let's just take an example of, say we wanted to modulate the z component, the x component, we wanted to modulate the z component as we move in the x direction. So what would we do for that? There's some sort of side-by-side coils, like one on the far and then one on the near. And if we turn on, it's much more complicated than that in real life, but this would give you something like that. So if you turn on those coils, it will add to the magnetic field, to the z component of the magnetic field, as you move in the x direction. So what does that mean? Well, imagine somebody, let's look at somebody in there, happy person being scanned. I'm really looking forward to being scanned. Smile. So here's the magnet. So you're looking at them from the top down. So top down. So if they just go in there, what will happen is, if you measure the magnetic field, there's just this huge magnetic field sort of coming off like this. No matter where you are, in their head, the magnetic field's all the same because you haven't turned the gradient coil on. Now, when you turn the gradient coil on, what happens is you add a little bit to that as a function of where you are in x. So this is the x direction. So this is x. So that's what the gradients do. So they tack on a little bit, not very much actually, like only about less than 1/100th of the main field. So I'm exaggerating how big it is. So so it adds a little bit on, and then it subtracts a little bit off on this side. So that's what the gradient does to the z. That's what the x gradient does to the z component, to the b0. So it just adds to the b0. So it modulates the z component of the b in a particular direction. And that's what makes the noise. So why does it make the noise? Well, I forgot to say, so then you might have like these are the coils that would make the y gradient, and then you have some coils in here that make the z gradient. You could change the z component in the z direction. So why does it make noise? Well, it's hooked up to three 1.5 million watt amplifiers. It would make a great stadium back in the day when we had stadiums, a stadium amplifier. And so these coils are not superconducting, so they have to be water cooled. So there's actually water circulating through these coils when they're running. But why do they make noise? They make noise because we power them up in order to generate this non-superconducting magnetic field, and since they're non-superconducting, they get hot, and so you have to cool them down, and you have to actually water cool the amplifiers too because they're so powerful. Now, when you power them up, they generate a magnetic field, and that causes some pushing of the coil. And then if you rapidly flip the gradient to the opposite direction, the coil will try to sort of like move back and forth a little bit. And so that sound you get is just rapidly going like back and forth like that and vibrating the coil. So that's what actually makes the noise. So that's number 2. And then number 3, we have to actually get a signal out of you. And so on a modern magnet, the main thing that injects something into you in order to get a signal out is the body RF coil. So there's another coil in here. You can't see this one either. This is another one in here. Okay, it's getting a little messy here, but it's slightly different color. So there's another coil in there. And that guy, let me just label these. So the B0 field is coming from these guys. And the gradient coils, I'll do it in green. The gradient coils are these guys. And then the body RF coil is inside of that. That's actually what forms the bore. So the actual bore that you sit in, that's actually, the RF coil is embedded in that. And so what does that do? So what that does, that just makes yet another magnetic field. And that magnetic field is perpendicular to this main magnetic field, the B0 magnetic field. And so if this is the B0 field, like this, you essentially have a extra magnetic field here, like this, that's rapidly rotating around perpendicular to the B field. And that component of the field is called the B1 field. So, no, but that's just a conceptual way of thinking about it, because at any point in space you just have one magnetic vector. So what does the body RF coil do? What it does is the B field is in the Z direction, so you got this really big long vector like this. That's the B0. And then you've got this extra vector tacked on top of it at some angle, say it's going that way. And that's the B1. But that's just sort of like a conceptual way of thinking about it. What's actually there, just B. So here's B. This is just plain old B. And what does plain old B do? Well, it just wiggles around. So when you turn on the body RF coil, all it does is it just causes a little sort of like a wiggling of the B field everywhere throughout the bore. So that's the B1 field. So B0 field, this is the B1 field. Just another magnetic field. It's all just one B field. And so we're almost to actually trying to get a signal. So that coil, that RF coil, will wiggle your protons a little bit. And then for about a tenth of a second, there'll be this little weak radio wave that will come out of your head from the wiggling protons. And so that comes out into yet another coil. So let's finally put the person in here. So here's the happy person. I'm happy. Scan me harder. Yeah. There. Happy person looking up. So how does this work? Well, there's typically these little coils like this inside the head coil. And so here's one, here's another one. Here's another one. So those guys are set up to detect this little weak radio wave that comes out of your head. So that's the in the old days they used to transmit and receive with the same coil, but it turns out to be better we'll talk about this in detail later on. It turns out to be a lot better for the signal, and it also allows you to accelerate your scans if you have smaller coils. So this is receive only head coil, or it could be a knee coil. So which is that guy? That guy was an orange. So let's put that guy there. Okay, so now we're getting a signal out that we actually can use. And there's one more set of coils before we give up on this. There's one more set of coils. They're actually inside the gradients, and these are called the shim coils. And shim, generally means to kind of get things in order. Like if some beam is a little bit too low, you stick a little shim under it to sort of straighten it out. So what the shim coils are trying to do is flatten out the B field. So flatten B field. So what does that mean? the B0 field. So what does flat mean? So flat just means the same everywhere in 3D. So you want to, in 3D, try to get the strength of the B field the same everywhere. Now, isn't it already the same everywhere because you designed the magnet that way? It is, but what happens is when you stick somebody into the magnet, it causes a distortion because if you stick a person into the magnet, they've only got a body on one side. There's all this magnetizable stuff in their body on one side, and then there's just air on the other side. So that causes the B0 field to get a little non-uniform. And so what the shim coils do is I won't draw them, there's another set of coils that are inside the gradient coils here, and you can turn them on, adjust them to try to make the field as uniform as possible after you put somebody in there. So that's called shimming. And so we'll talk about that again in detail later. So one thing I mentioned is when we turn on the RF field, that's adding on to the B field, but it's pretty small. Same way with the gradient coils. So the gradient coils, our gradient coils can do 80 millitesla per meter. So what that means is that over 1 meter, over 3 feet, they can change the strength of the Z field by 80 millitesla. So that's 100 millitesla is 1/10 of a Tesla. So, but we never turn it up that far. Usually we're much lower than that. And so the field is 3 Tesla. So you can see we're just adding a small fraction onto the really big B0 field. Even making all that noise using 3 1.5 million watt amplifiers. Okay, so that's the hardware. That's the basic hardware. Not too complicated, but it's got 3D, and that's the 3D is kind of what gets you. So what we want to do now is talk about quantum mechanics just a little bit. So to try to get an idea about what is the signal that we're creating, this precession business. So quantum mechanics was developed in the early part of the century to try to explain how atoms behave. I mean, the idea of an atom is very old because people, even before quantum mechanics, people knew that there had to be something like atoms because of studying chemistry, studying how compounds interact with each other. You knew that there had to be down at the bottom, you knew there had to be things that were all the same size, like certain kinds of, gold, like a gold or a sodium atom. They all had to be the same size. So the idea of sort of quantumness, or sort of same-sizeness, that's a really old idea. That predates quantum mechanics, but at the beginning of the century, they worked out this theory. It works really well. A lot of physicists, they kind of don't like it. Einstein didn't like it. He really hated quantum mechanics. Schrödinger didn't like quantum mechanics. He invented it. He was the Schrödinger equation. He didn't like quantum mechanics. So why didn't he like it? Well, the way the theory works, you have something like the Schrödinger equation. In the Schrödinger equation, you have this differential equation. It sort of tells you how things change over a very small amount of time in space and time. And you solve it. So here's a solution to the, solution to Schrödinger. It extends across space. And so the first thing is that at each point in space, it's a complex number. So it has 2 components. There's like a vector at each point in space. Okay, so that's kind of weird. But what you do is you square it, and then you square this, the wave function, this solution that you have to the Schrodinger equation. So you square it, and then you get a probability, a real number that's a probability. You get rid of the imaginary part. And then what does that tell you? That tells you the probability that something is here. So it's higher probability it's over here than it is over here. And then what do? You do a measurement. And so when you do a measurement, say I figured out it's actually right there in one dimension. And so then what happens in the theory, the way that you essentially solve the Schrodinger equation at an instant in time. You get this complex valued function, you square it, then you get the probability, then you make a measurement. And then the way the theory works is it says, okay, now the wave function is right there. It's just a point right there because we actually measured it, and that's where it is. That's not in the equation, actually. That's just like, a measurement happens, and then suddenly the wave function is just slammed to a point. And then you run the Schrodinger equation solution through time, and then this thing starts spreading out, and before long you get another spread out thing. So that's just the way it works. There's been many attempts to try to get around this. Einstein spent his whole later part of his life trying to get around this, but it works. And so what are some of the, without doing any math, except for very simple sort of top math, what are some of the basic observations that forced people into this view? And so one basic thing was an experiment called that relates to spin and precession, was the Stern-Gerlach experiment. And so for this experiment, what they did was they just got a really strong magnet, and then they got some silver atoms and just shot them through the strong magnet. Now, these were neutral silver atoms, so they weren't charged. They had sort of electrons and protons, and so they weren't charged. But what happened was, when they went through the magnet, instead of just sort of spreading into just a distribution, they just spread into two points, just sort of up and down. So you would think, like the silver atoms, they had some little magnetization, but those magnetizations would be in all different directions. And when you shot them through here, what you might expect is that depending on what direction they were, they would sort of go make a whole distribution of different directions. But instead, what happens is they just sort of go up or down relative to the magnetic field. And so that's weird. So if you look at, if we imagine, so why do they call it spin? So if we imagine we've got like a little sort of little sphere, a little atom sphere, and it's got a charge stuck to it, and that charge is rotating around, well, then you're going to have, a sort of rotating around current generating a magnetic field that points up, and so you'll get a magnetic field sticking out like this. So you'll get they'll look like a little magnetic field. The spin around the axis will generate a magnetic field along the axis. So they behave like that, but then they've got this weird property that when you run them through a strong magnetic field to polarize them, instead of just going in every which way, they just go two ways. So that's the quantum aspect. And so if we actually look at, if we make a big diagram here of three different conditions. So we'll start off with no strong magnetic field. So no strong. So this is B. The B0 field equals 0. No strong mag. And then we have two different views of this. So the two different views of this are, the first view is the microscopic I can't spell, microscopic view, and this is the macroscopic, like voxel picture, macroscopic voxel. Okay, so here's all the little proton magnets. They're just all pointed in every which way, like this. They're all sort of disorganized. So they're all same length, but random directions. So if you add them all up, so if we imagine we've got some voxels now that are like 1 millimeter voxels or something, and if we add up all those vectors, since they're randomly in all different directions, tip to tail, we just end up with 0 everywhere. So there's a lot of magnetization in your brain. Every atom is like a little magnet, but since they're all in random directions, they just all add up to 0. So if you try to measure the magnetic field, if you're just sitting there, you don't have any magnetic field. So this one's called the bulk. Sometimes we call this the bulk magnetization. Bulk mag equals 0, because it all got canceled out. So now let's examine what happens when you go in the magnet, but you haven't turned on the RF coil. So this is just the strong, magnetic field. So here's B0. And now I'm going to do the thing I said, like in real life, the strong magnetic field is running horizontally parallel to the floor, but now I'm going to draw it. Now I'm going to draw it up because it's often drawn that way. So here's the B0. The B0 is up in this direction. So what happens now, sort of the quantum thing that happens, is that the vectors, these same size magnetic field vectors, these are supposed to be the same as they are down here, so let me lengthen these a little bit so that so everything is consistent here. Okay, there we go. So now what happens is they orient themselves relative to the B0 field. But they've got this strange property, since they're quantum, they're always at an angle of 54.4 degrees relative to the magnetic field. Or they're at negative 54.4 degrees. So they basically will sort of be like 54 this way, so like, 54.4 that way, or 54 the other way. That's just, and you can sort of see that with the Stern-Gerlach experiment. They're just flip into one direction or flip into the other direction. That's the only possibilities. But they can be at sort of random locations around the circle. Now, the thing is, they're already precessing. So they're already precessing. But they're all disorganized. They're all precessing in different directions and different, not different directions, but different spacings along the circle. And so they're already precessing, but since the XY components, the XY component in the XY plane is random, the XY components all cancel out. So XY cancel, but the Z component doesn't. The Z component, because the field is up, there's more up. Slightly more up. slightly more up. So how many? It's like 3 parts per million, not very many. So you're not a very good magnet. If you lined up all your protons, you'd be like a really good magnet. You could pick up a car or something, but we're not a very good magnet. Just 3 parts per million more going up, lined up with the field than not. So there's a Z bias, but the XY cancels out. So if we go back to this picture, what we end up with is a little bit of magnetization in the direction of the B0 field across your entire head. And what's it caused by? These protons that are stubbornly, they're all precessing around at 54 degrees or minus 54 degrees. There's a few more of them up. The XYs cancel out. You end up with this bulk magnetization. Okay, so last but not least, what happens if we, apply so we got strong B0 plus oscillating, rotating, let's say it's rotating B1. So now what happens is, you can sort of visualize this as you're causing them to bunch up. So that they're already all precessing, but we can't see it. And so what happens now is there's still some over here and some over here, but now there's more of them bunched up like this, so like on this way, and then similarly down here, the same thing. There's more of them sort of bunched up over here. There's still ones in all different directions, but there's some bunching occurred. You kind of like swept them into alignment with this field. So what is that field? Well, that's the B0 field, B1 field. So here's the B1 field that's sort of going around in that direction. So that's the rotating B1 field. So this guy is the B1, but it's rapidly rotating around. In real life, it's rotating around in a vertical plane, but now we've rotated the B0 to be up and down, and so it's rotating around this plane. So it bunches up the vectors, and so now there could still be more of them in this direction. It's possible to get more of them in the down direction, depending on how strong we turned on the RF. But you can sort of, if you add them all up, what are you going to get? Well, if this is a plane here, say there's more in the up direction, you'll end up with a resultant vector that's sort of slightly off the plane. It's sort of slightly lifted off the plane. And that resultant vector is precessing. And so if we look at that across time, what happens? So here's several little time points. So time t equals 0, t equals 1, t equals 2. Here's that vector, and that sum vector is precessing around in this direction. And then here's a little bit later point in time. Now it's over here. It's going around that way. And then here's a little bit later. Now it's over here. It's going around that way. So the summed bulk vector precesses, just for like 1/10 of a second. And so what happens is, after a while, it just goes back to this state where they're all lined up again. So that's the fundamental signal that's coming out. That's the basis of everything that we record, is this temporary sort of alignment of all these precessing spins. So what is the equation for that? It's actually very similar to the equation for a top. And so it's a really simple equation. So it's just 2 pi frequency of precession. We'll put 0 for, we haven't messed with the gradients, and so we just have the B0 on. And so this is cycles per second. But you can also write frequency with that symbol, with an omega symbol, which means radians per second. And so what's the difference? So immediately, we've got to get into the units a little bit. So this guy is cycles per second of precession, not spin. So it's like a top, and I'll talk about a top in just a second. So this is radians per second of the same thing. So what's a radian? Well, radian is, we have a circle of radius 1, and if you just go 1 along, so if you just go 1 along the circumference, that angle is a radian. So, so we have to multiply by, there's 2 pi radians going all the way around the circle. So you always go back and forth between cycles per second, which is kind of intuitive, like 1 cycle per second. Radians per second is less intuitive, but then you don't have this 2 pi business in there. Okay, so that's the frequency of precession, cycles per second. So cycles per second at 3 Tesla, this is going to be, or 2.9 Tesla, this is going to be 123 megahertz, so 123 million cycles per second. And so what does that equal to? So this is one of the first very simple equations. A constant, that thing is a constant, gamma, the gyromagnetic ratio, times B, the strength of the B0. So that's not a vector, this is just the strength of the B0. This is the magnitude of B0. And this guy's just a constant. Gyromagnetic ratio. So that's really easy. All that says is that whatever you set the B0, that just tells you what the frequency of precession is. It's much easier. It turns out this is actually considerably easier than a top. So you often make an analogy between these protons and a top. And so what's the equation for a top? So the equation for a top is more complicated. So the equation for a top is, so here's the equation for a top. So what's the frequency of precession of a top? So what is a top? A lot of people haven't even seen a top. So a top, like back in the day, we used to have these tops. They've got a little spike on it like that. You wrap a string around it. You wrap a string around it, and then it's dangerous, like I say, it's dangerous with the learning glass, and you throw it down and whip back the string, and the top will spin very rapidly. So the top will be spinning very rapidly that way. That's the spin. But then if you look at the movement of the top top sort of precesses around this way like that. So at a later point in time, the top will be over here. So that's the movement of the protons that we're talking about. This slower movement, slower precession movement of the top around in a circle like that. So what's the equation for that for a top? It turns out to be more difficult. So so if here's our top, so our very simple top. So it's got some mass there, and there's a certain distance out to that mass. So now we've got to include a lot more things in it. So how far is the weight of the top from the point where it's touching the ground? How much does it weigh? The gravitational constant, that's the thing that's like the B0. And then we have to divide it by the angular momentum. The angular momentum is going to be the moment of inertia. That's kind of how spread out the top is. Like, it'll be different if you've got like a spread out top versus a really compact top. And then finally, the spin, the actual spin. So here's the rate of spin of the top. So, and if you just look at this, when you have simple equations like this, we didn't derive it or anything, but just look at the equation. The good thing to do is always just fiddle with it. Like, so what happens if I turn the spin up? I spin the top faster. That's in the denominator, so that means that the precession of the top, so this is the precession And this guy's that guy's the spin. The precession at the top will get slower because as you turn this number up in the denominator, you get a smaller number. And that makes sense so for instance, if the top slows down as it runs down, it starts to precess more and more rapidly. And then the moment of inertia, well, you change different size tops, it affects it. If you make the top taller, it makes it precess faster. If you make it heavier, it makes it precess faster. So it turns out this is actually much harder than quantum mechanics. But if you sort of like take all these guys, because they're all constant, that's sort of like the gyromagnetic ratio. That's like this guy. And then the gravitational strength, that's like the B0. So you can see that the tops, the little proton tops are much simpler. Quantum mechanics is actually simpler. It's just exactly proportional to the strength of the B field. And the very last equation is also simpler than it would be for macroscopic tops. And that equation is, how much magnetization do you get? And it turns out the amount of magnetization you get is pretty much just proportional to how much stuff you have and what the B0 field is. So this last equation here, so we did a very simple equation, harder equation for the top, and here's our last equation. So our last equation is the magnetization in the z direction after you've been in the magnet for a couple seconds. And what does that equal to? That equals to, let's take whatever the magnetization is, the magnetization vector, and then this symbol just means find the length. So it's just the amplitude. So the vector, three-dimensional vector, pointing in some direction. If we just measure the length of that, that's what this symbol means. So just take the length of that vector, and what the length of that vector is just equal to the gyromagnetic ratio squared times Planck's constant squared. There's only two things in here. So the B0, the strength of the B0 field, and the number of spins. And then there's 4 times the Boltzmann constant, and then the temperature of the sample. But like I always say, as long as you're alive, your temperature is basically the same. So the only variables in here are just this guy and this guy. And so what that says is the amount that you'll get magnetized is also incredibly simple. All it says is the strength of the magnetization when you go in there, the strength of this bias of more in the direction of the B0 field than opposite the B0 field is just whatever you set the B field to times the number of spins. So the number of spins is just how much stuff is in there. So it's very simple, extremely simple equation. So that's our last equation. Okay, and so now we've finished quantum mechanics. So the rest of the course, no quantum mechanics. This is just the sort of a very kind of messy introduction to what we think the signal comes from. So it comes from this protons. You stick them in a strong magnetic field. They get biased, but their phase or their position around that circle is all randomized, and they always have this weird sort of, they insist on being just like 54.4 this way or 54 point that way. It's just the way they are. And then we add a perpendicular field, rotating perpendicular field causes them to bunch up, and then that gives us a rotating signal that we can actually measure for a little while. But then before long, they get all sort of like, out of phase with each other, and then we just go back to this condition. So that's just the basic sort of basic Bowdlerized introduction to where the signal comes from. And so don't mix up sort of precession with spin. So spin is the thing that causes the little magnet to form in the proton. And then precession is how that magnet more slowly rotates around relative to a magnetic field, similar to a top rotating around its axis, but then more slowly rotating around the direction of gravity. So that's what a top does. A top does, it rotates around. You can tell from a top which way the gravity is pointing. The gravity is pointing down because the top is kind of rotating around it. Okay, so I'll email out the Zoom link for the live question and answer session at 8 o'clock, 8 a.m. this Friday. So we'll see you then live.